Mindsetters, welcome to our Physical Sciences show. Today we have a special revision lesson on physics. Make sure you have your notes and let the learning begin.
So first of all, what is a quantity? Now, a lot of you have heard this word quantity before, but you're kind of like, it's something that my math teacher says or it's something that my science teacher says. Let's actually start to deal with the word quantity. Now, quantity is anything which I can measure which uses numbers. It's all about the numbers. Now, earlier on, I started talking to you about how many Facebook likes we had. How many was it again? 50,000?
It's 50,079. Not 500,000 though, I'm just still too ambitious.
Okay, well, we're going to get there. We're going to get there. Just
Soon.
bring your family, bring your sisters, brothers, mothers, whatever. Just bring them and get the page liked and spread it out on Facebook. Even share our page. That would be great. Okay, so now we're going to start dealing with quantities, and quantities is what it's all about here. Now, a quantity is anything which you can describe in terms of numbers. So I'm going to give you some examples. I mean, you can talk about 40 girls, 50 boys. You can talk about 2 lumps of cheese. Anything you can put a number to is a quantity. So guys, you've been dealing with quantities your entire life. Now, anything which I say, okay, well, what is the quantity of mass? What is the quantity of my weight? These are numbers which I start to talk about. How many days until the weekend is something you're asking yourself. That is a quantity itself. It's something which I can measure with a number. So anything with numbers is called a quantity. Now, you might hear this a little bit later on in science, but when you start to talk about quantitative, now that's a lot of syllables. Okay, let's talk about this word, quantitative. Quantitative means to measure using numbers. So when you do a quantitative analysis, or if you talk about a quantitative theory, it just means that I'm trying to find out how much of something I've got. So now here we go. We start to take a look at our numbers, and it's how much we have of this quantity. Now, this is a word which is infamous. Guys, it scares matrics, and it really doesn't have to. Here it is. The quantity, and this is my magnitude. That's how much I have of something. So now, if somebody walks up to you one day and you say, you know, what is the magnitude of, let's say, for instance, the distance to school? And you start to scratch your head and you say, okay, well, I don't know what you're talking about. It sounds like magnets, and what's that got to do with school? Magnitude is how much I have of something. So your magnitude is just the size of your quantity. So anytime you start to talk about magnets, it just means how much, guys. All right, so I would like to have a large magnitude of money in my bank account one day. So that's one way to start striving for this. Guys, you should strive for a large magnitude of marks at the end of the term. It's just talking about how much I have of that particular number. Now, at all cases, I'm going to be running you through a couple of examples, explaining some of the words again. So don't worry about scribbling down furious notes. Let's start taking a look at some of the other words here. Okay, now this is something else which a lot of people don't pay enough attention to. Anytime I've got a magnitude, there's something that comes after this, and that is the question of units. And you might say, okay, well, sure. Phil, just slow down on the language here. Magnitude is how much I have. A unit is what identifies what magnitude I'm talking about. Now, let me give you a little bit of an example. If I was to walk up to you and I was to say to you, I have 15, and immediately your mind starts to go, okay, well, you got 15 what? 15 of chickens, 15 of eggs, 15 of cars, I hope one day. But start to think about this. You need to give a unit, and in all of those, I gave a unit. Oh, I have 15 kilograms of something. If I have 15 kilograms of sand, I can build something. 15 bricks. What I've been doing is I've been identifying what I'm talking about. So units are unbelievably important. A lot of grade 10 say, I don't have to substitute them. I don't have to put them down. It's not an issue for the calculation. But guys, units tell me what you've got. If I see an exam paper in front of me and I just see an answer with just a number, I cannot give that answer correct tick without a correct unit, because I have no idea what that number is. If somebody says to you, no, the answer is equal to 1, okay, well, that might be useful for simplification in maths, but if I'm talking about some children, it would be really nice to know if I have a whole person or if I've got half a person, which is very bad. Okay, so now let's start talking about the magnitude and how they deal with units. So let's start taking a look at an example of a quantity that we all use. Guys, you already have been dealing with this quantity, and all of us do all day, every day. Okay, so let's start taking a look at what we've got in terms of a quantity. My example, because it's probably the most common example, is this stuff, time. Guys, the clock is always ticking. It's something which I'm always short of. I describe it in many ways. I govern my day by time. This is the reason that I've chosen time as my quantity. I can measure time using numbers. Guys, if you lift up, look at your watch, look at your cell phone, you can measure the time. You've actually got a time measuring device in front of you. Now, let's take a little bit of a step back and let's start to see how we would actually describe what time is in front of us. So if my sister or my brother or my mother or father come up to me and say, Phil, what is the time? Or how much time do I have left? Or how long should I cook this pasta or this egg or this toasted sandwich for? Right. What I can do to them is I can say, okay, well, you need this much time. Now, in physics, what we've got to do is we've got to get a little bit more specific. So now I'm going to introduce you, if you haven't already, guys, I'm going to introduce you to the little bits and pieces of the way that we use quantities in physics. Okay, so first and foremost, you might say, okay, well, Phil, there's a lot of letters over there. I thought I was looking for numbers. There's two different letters over here. One letter over here on the left and one letter over here on the right. Now you might say, why are there two different letters? This is very confusing. Let me explain this. Okay, now my symbol represents the quantity that I've got. T is for time. Okay, now you might say, okay, well, I don't have 350 times. I've got something in terms of units, and that's what the other number is for. On the right-hand side here, I've got S, and that is for seconds. Now that identifies that I'm dealing with time. So if I was to walk up to you and say, how long is this meant to take? 350 seconds, you would understand what I was saying. Kind of an unusual length of time, but in physics this is quite common. Now let's deal with the difference between these two. Now when I see an equation, I'll use a symbol. This is the thing which I put into an equation, and this is the thing which I find in time equations. How I give my answer or how I deal with the actual magnitude, I use my unit. Now let's get to the really important part of what's on your screen at the moment. The 350, this tells me how much I have. Now if you remember a little bit earlier on in this show, I used the word magnitude to show me how much of something I actually have. How many seconds do I have? I have 350 seconds. This might seem, oh, Phil, this is really simple. But you wouldn't believe how many matrics still ask me, what is the meaning of the word magnitude? So if something is of great magnitude, there's a lot of it. There are many seconds. It has a great magnitude. So I want you to get comfortable with the language as we go, because I'm going to start throwing it around quite quickly. I want to make sure you stay with us. A vector quantity has got magnitude, and this is the really, really important thing, direction. You might say, okay, well, Phil, how do you put in a direction into a unit? I mean, do you just say temperature here, have some direction? No, absolutely not. Okay, what you've got to do is you've got to realize that some units need direction to give them some sort of meaning. Now, here's an example for you. This is just to give you an example of why direction is so important. If I tell you to stand up and walk 50 meters, you're going to say, oh, well, that's not going to work. If I stand up from my couch or from the floor or from the table where I'm watching TV at the moment, I'm going to bump into things. And where should I go once I get out the door, if I get out the door? Direction means a lot, especially when we're starting to move. And guys, next week, it's all going to be about motion. So it's vitally important that some units have got direction. It might actually surprise you which units have direction in them. Now, what I'm actually going to do is I'm going to discuss the symbol, the unit, and how I describe the direction. Now you might say, okay, well, I can see this for distance. Okay, stand up, walk 50 meters forward. All of a sudden, no longer are we talking about distance. It's a separate unit. It's no longer distance. It's displacement. And we're going to talk about these words in a moment, especially next week when they become important. So now, let's start to talk about that one, which some of you are a little bit afraid. I see that bathroom scale in there in the morning, and I sort of climb on, and I close my eyes, and I hope for the best, and I look down. What am I measuring? A lot of you think, okay, well, I'm measuring my weight. But guys, what's on the scale is measuring kilograms. This is very confusing. Now this is where some of the confusion comes in. If I say that I have a large mass, I also have a large weight. But now, what is the confusion between these two? Now, weight is a force, guys. Weight is how strongly the earth is attracting you. There we go. So weight is a force, and sometimes it's Fg. And you might say, why is it not W? Now, we're trying to move away from W for weight for one simple reason. It's because there's another quantity which also has the symbol of W, and that is work. So these things can get very easily confused between the two. So it's better to say force, gravity. Now the force, gravity, has got a unit, and you might say, okay, well, I don't have a weight down. But guys, absolutely you do. This is one of the reasons when I fall out of bed that I fall down. The direction of weight is always towards earth. It's always down, wherever down is for me. So weight is an example of a vector quantity. I feel a certain force down onto earth, and it's always in a certain direction. It's very important that it has direction. If I fell upwards, we'd all fly into space. Weight definitely is a vector, guys. It has a magnitude which I can measure in newtons, and I can describe that it's a force downwards. I hope that you can see the difference between a vector quantity and a scalar quantity. Now, all quantities can be separated into those two things. Ones without direction can be classed as scalar. So they're just things which I measure up with numbers. I'm just going to go back to that spreadsheet that we were talking about a little bit earlier on this table. All of these didn't need direction. Now, if I was to say to you, okay, well, if I say to you, I need 15 moles of sulfur forward, you'd be very confused. Okay, I'm confused saying that. If I say to you, I go 15 seconds up, it's a very strange thing to attach direction to any one of these. And if I say to you, okay, it's 5 degrees to the right today, and a lot of you are saying, okay, well, I'm not dealing with trigonometry here, I'm talking about temperature in Celsius. All of these don't have any direction. This is what makes them a scalar quantity. Scalar quantities don't have a direction. Now let's take a look at some of the other vectors. I hope that you guys are filling in ahead of me. These vectors have all got directions. Now we're going to fill this in together. Displacement has got an unusual symbol, and that's the symbol of x. Now you might say, okay, well, Phil, why does displacement, and what is displacement, and why does it have this strange symbol of x? Okay, well, distance is the cousin of displacement. So displacement and distance go together. Now, if I say to you, stand up and walk 5 meters, what I've given you is a distance which I want you to walk. I haven't told you where. So that is a distance. When I deal with displacement, I need to add a direction. If I was to say to you, okay, well, stand up and walk 5 meters towards the fridge, all of a sudden now you've got a place to go and you know exactly where you're going. And that is displacement. But again, why the symbol x? Why am I using x to describe displacement? Well, guys, think about maths. When you've got a flat Cartesian plane, the x-axis is the horizontal one. Now, sometimes things move up and down, and I describe their displacement as y. So now we'll get to y later on and perhaps even next year. But displacement in terms of x just means how far did I move across the ground. Now, this is the important part, in a particular direction. That makes it into a vector. Now, this next one, you might recognize this, but before we go there, let's talk about displacements units. This tells me that this is related to distance, and it's measured in meters. Now, velocity, I see has got a unit which I've seen before. I can measure velocity in meters per second. That sounds a lot like speed. However, the difference between velocity and speed, I'm hoping that you've managed to guess it, is that speed is a scalar, while velocity is a vector. Now, if I was to say to you, I was heading at 50 meters per second, that's very, very fast, 180 kilometers per hour. If I was traveling at 50 meters per second, and you say, okay, well, where were you going? The minute I add direction to it, it becomes a vector. If I said I was moving 50 meters per second towards the coast because I wanted to go on holiday and I got pulled over by a speed cop, that's very, very dangerous. But this velocity over here is measured in the same units as speed. However, I need to add a direction. So all of these need to add direction. Now let's deal with this next one. Acceleration, most of you have dealt with that before. Measured in meters per second squared, also needs direction. Now, some of you might say, okay, well, I've never dealt with acceleration before. Now, most of you have picked up an object before and dropped it to the ground. Everybody has done that. An object which was stationary in your hand started to accelerate towards the ground. Now, I challenge you, and I really, really do challenge you. I want you to discuss this on your page, to try find an object which accelerates in the opposite direction to gravity that doesn't have an engine or a motor or something pushing it upwards. So most objects, I mean, the saying goes, what goes up must go down. Now, if I launch this thing up, it's going to go down eventually. Gravity always acts in the same direction, guys, and that is its acceleration acting. The acceleration of objects towards the Earth is a constant. Okay, and then this next one. This is a word which we're going to say for next year, but momentum as well is dependent on velocity. Now, the only reason that I put in momentum is because momentum is the amount of motion that something has. That also depends on the direction of this motion.
Okay guys, I hope you are enjoying this revision session. If you are struggling and need help, remember to post on the Facebook page, facebook.com/learnextra. Now it's time for a break, so don't go away. We'll be right back. Welcome back, guys. I hope you are getting into the idea of revision. Please let us know how you are doing. I'd love to chat to you on Facebook and on Twitter. Enough of the chat. Let's get back to revision.
Now what I'm going to show you now is called the head to tail method of adding vectors. So a lot of you on the Kiro page are really struggling with this. Now you can join up arrows one after each other. The head of one arrow should meet with the tail of the other. So now these arrows have to be joined, and this is actually the name of the method. It's called head to tail. That means the tail of one should start at the head of the last one. Notice how those two arrows are actually touching each other with the head of one and the tail of the last one. Then we find the distance from the beginning of the first to the end of the last arrow. Now that sounds hugely complicated, but I'm going to use these two little pink arrows and I'm going to draw in a green arrow. The green arrow is going to represent what we achieved. What was the end result of what we did? That meant that I ended up somewhere over here. If I walked up and to the right, I would have ended up in the place where the green arrow is showing me. But I can't leave it like that, guys. You've got to be a lot more specific. Now, this green line is called the resultant. The resultant is the end sum. When you've added together all the vectors, the resultant is what comes out. Now, guys, I know that some textbooks say sometimes the resultant, you've got to subtract things. Guys, the resultant is always a sum. It's the total of all of your actions. If I walk 2 steps forward and 1 step back, what is the total of my efforts? Now, what you'll find is you'll say, okay, well, that's 2 minus 1. That means that I land up 1 step away from where I was. Okay, you're doing that mentally. Now, let's do this graphically together. Okay, so now I'm going to introduce the idea of different types of direction over here. So I got my ruler ready. I hope you've got this right. But now, I've got a major problem over here. It says that someone walks 30 meters north and then 40 meters east. There's 2 vectors. How do I do that? Well, guys, I've got to use that same scale again, and I've done 30 meters before. That means that I'm going to draw a line which is 3 centimeters. How do I do 40 meters? You guys guessed it. That's 4 centimeters. What is their final resultant? So where did they land up? So this is what I'm after. This is always what I'm after when I'm dealing with vectors and simple addition. Okay, so guys, I'm going to hold your hand here. The first thing that you're going to do is, because we're talking about north and east, I need a reference of cardinal points. Now that sounds way more fancy than it actually is. What I want you to do when you're trying to do cardinal points is I want you to make a compass. Guys, a compass has got your 4 points over there. Your compass is always your starting point when you've got questions of north, east, south, west. So there's my north, there's my east, there's my south and west. Hopefully you guys have got this down. Okay, but now what I'm going to do is I'm going to use my compass, the center of it, as a starting point. So now this person, if I put my zero of my ruler over there, this person walks 30 meters north. So what I've got to do now is I've got to draw a line which goes up 3 centimeters up the north line. So let's do exactly that. Let's rotate our ruler around so it's facing directly north, and let's draw something. Let's just make sure that's nice and north. It's fighting me today. There we go. All right, so we got a nice north-facing ruler. Now let's draw ourselves a 3 centimeter ruler. So now, I don't know if you can see the numbers on there, but I'm going to actually read them out as I go. I'm going to start out over here. So down at the bottom, I'm going to draw all the way up. Right, so there we go. We've got 3 centimeters drawn up there, and we can move our ruler away. And let's just make sure that that ends in a head to show me that this person walked 30 meters north. There we go. Now what we're going to do is we're going to allow this person from that new position to walk 40 meters to the east. Okay, so now what I've got to do is I don't go back to my start. That's not possible. I can't start from the beginning again. Now what I do is I apply the head to tail method. I've got the head of the original arrow, and I've got the tail of the one that I'm about to draw. So there we go. I've got now a ruler which faces directly east. If you really want to, you can do this with the protractor or that right square inside your math set to make sure that you've got a nice 90 degrees. But I'm just going to do this by eye. But at the moment, I can see that that is starting at the head of my original vector. Now what I'm going to do is I'm going to draw in my new vector of 40 meters to the east. So let's do this. So let's draw in another vector. I've got a vector which starts at the head of the one, follows through. So there's 2, 3, 4 centimeters over there. Fantastic. We've drawn in our new vector. Let's just make sure that there's a nice head on the end of it. Right, and that represents 40 meters to the east. Now the question is, where's the resultant? Now, remember what I said. You start right at the beginning of the story and you find out where the end is. So what I'm going to do now is I'm going to use my ruler to do exactly that. So I'll show you exactly what I'm after. I want to put my ruler where I began. So that's where I start. So this is the beginning of our story. This person that's about to walk 30 meters, then 40 meters. Now I'm going to close a triangle over here. Now it's not always a triangle, but what you can do now is you can say, okay, I'm going to rotate my ruler around, and I'm actually going to find something very interesting if I do this. And it's not actually all that clear over there. I'm not sure if you can actually read that off there, but what I'm actually finding is that there's a very interesting resultant. It shouldn't be a surprising resultant at all. If I start there, let's make that a nice bright color over there. So we're starting at the beginning there, and I'm drawing in my resultant over there, and I measure it, guys. What I'll find is that the length of this one with my ruler, and I'm hoping you're doing this at home, is 5 centimeters. That's very interesting. Why 5 centimeters? Because that works out to be 50 meters. Now guys, I hope that you've seen this ratio of 4 to 3 to 5 before, because guys, this is a Pythagoras triangle, because look, I've got a 90 degree over here. So I can say that my resultant is 50 meters, but now I need to give it a direction. And guys, here's your challenge. You need to measure it from the north. Any diagram where you measure the degrees clockwise from north is called your bearing. I know that this is something that people really struggle with, but when you start at north and you measure clockwise from north, that is your bearing. So guys, I want you to try and state this, and I'm going to look on the Facebook page for 50 meters, and I want the bearing of this, guys. What I'm going to ask you to do is I want you to work with us, and what we're going to do is we're actually going to measure out the path. Now, I've chosen 2 particular places around here in the surrounding blocks, and we're actually going to measure them out together. So what I'm going to ask you to do is to get from point A to point B. So now, guys, I want to make sure that you can work with your rulers and actually work with the maps, and we can actually see what goes on here. Okay, now, I said I want to go from point A to point B. Now, unless you're a bird or you've got your own helicopter, you guys cannot fly over a block. Okay, now the reason I point out those 2 examples is because I'm actually going to use that in a moment. So what I'm going to do is I'm now going to plot out a path to get from point A to point B. Now, there's a few ways we can do this. So what I'm going to do is I'm going to draw out the two pieces, the two parts. So I'm going to start out, there's my first leg of my journey. I travel first down Main Avenue to get to that corner. Then the most direct way to get to these corners, and this is just down the street from us, is I can plot out a second part to my journey, which is all the way over there. So what I'm actually going to do is now I can start to measure out the parts of my journey. So the way that you can start to do that, and I'm actually going to bring up another ruler here. It's, there we go. All right, now I want you to grab that ruler that I told you to get out. So here we go, I've got my ruler ready. So now what I'm going to do is I'm going to use my ruler to scale out my map. Now, the way that you do this is you start to line up your ruler the same way that I'm doing this, and we're going to start to measure out the path on here. Now, you might notice I've actually got the wrong part of the ruler there. You'll notice that some rulers are measuring in inches, and you're going to be measuring in centimeters. Oh, it's horrible, confusing. Make sure that you're using the correct side of your ruler. Now, this ruler can measure both millimeters and inches. Guys, we want millimeters. Okay, so now what I'm going to do is I'm going to measure out that first part, that first leg. Later on, I'll be calling this a component. Guys, if you remember from last week when I started adding together vectors, I started to call them components. So let's measure out our first leg. Let's measure out the first part of our journey. Okay, so now what I'm going to do is I'm going to say, okay, well, I'm going to put the 0 on my starting point, which is A. I see that I move 85 millimeters along this map. All right, so now the question is, how do we actually start to deal with that in terms of scale? Now, I'm going to practice with the scale, and we're going to try and change 85 millimeters into an actual distance. Now, I said that my scale, and I'd measured this a little bit earlier on, I found that on my map was that every 25 millimeters represented, and sorry, that's actually a mistake there, that's 100 meters. That's not 100 millimeters. Okay, so now my scale is 25 millimeters on my map to 100 meters in real life. It wouldn't be 100 millimeters or we'd never get anywhere. Okay, so there we go. So 25 millimeters on my map represents 100 meters in real life. Now, how do I scale 25 into 85? And you say, oh, this is a little bit difficult. So what do I do? Okay, now I've got my scale here. Let's write down my scale together. Now, there's a certain way of laying out your scale which actually makes life a lot easier. So 25 millimeters has a ratio to 100 meters. Now, you lay out your scale that way. Now let's put in the numbers that we'd like to scale. So which one do I have? Do I have the map size or do I have the real size? I have the map size. So what I'm going to do is I'm going to put map underneath map, and then I'm going to put real underneath real. Okay, now I'm going to show you how to work with these ratios, because a lot of grade 10s really struggle with ratios and when they deal with the vector diagrams. So let's write in a different color to show you the new information. I measured out on my map that I moved 85 millimeters. So that's what the ruler told me. I would like to know what is the real distance that I moved. Okay, well, the question is how to actually work with these. Now, here's one of the clues. Anytime you've got two of the same, now there's a way to move around here. I want to move from here, around here, and end up here. Now, if you have two of the same, I want to get rid of the millimeters. I want to make sure that they cancel out. The only way to do that is to divide. If you're going up or down, you divide. So here goes my sum. So I start out with 85. I divide by 25, and that gets rid of the millimeters, because the millimeters will cancel out. So I divide by the thing which I have. Then I multiply by the thing which I want. So you multiply to go across here. So I divide to go up, and you multiply to go across. So you multiply by 100. And let's put that into the calculator, and let's see what comes out here. So I grab my wonderful Casio calculator, and I say, all right, I'm going to start out with 85. And then what I'm going to do is I'm going to divide by 25. So there's my answer, and then I multiply that by 100. And that will get me an answer now in meters. So that is 340 meters. That was the length of my first trip. Okay, so that tells me that I moved 340 meters. Let's mark that on the map, because last week I told you that you should write onto your map the real distances. So that was 340 meters, the first part of my journey. But I went further. I turned left once I reached there. So what I'm going to do now is I'm going to move my ruler, and we're going to measure the second part of this. So we actually need to change where we're going there. There we go. We can actually flip this right around. Let's make sure that our 0 is on the next part. Okay, so guys, your ruler is a little bit easier to move around than mine, but there we go. There we go. That's what we're looking for. All right. So if I measure from 0 over there, I measure another 140 millimeters. So I hope that you can measure exactly the same thing. So 140 millimeters. Guys, this map is in the notes. They're free. They're on the website. So now 140 millimeters over there. Okay, now we're going to change 140 millimeters, and we're going to see if you guys can do the scaling yourself. So I want to change 140 millimeters. So I'll start out with 140 millimeters. There's my two ratios. Remember that you write them together. So 25 millimeters changes to 100 meters in real life. So there's my map sizes. There's my real sizes. Now remember that moving up and down is divide. So you take 140, divide by 25, multiply by 100, and that should get us to our answer. So you divide there, and to move across, you multiply. That's always the rule for your ratio. It's a really nice, easy way to do this. Okay, so now let's do exactly that. So I take 140, I divide by the thing which I have to get rid of it in terms of millimeters. I don't want millimeters, I want the meters in real life. Then I'm going to multiply by 100. And that lands up being, so let's take a look at what we've got here. Let's clear. So 140 divided by 25, and that gets us an answer of 28 over 5, multiply by 100, and that'll get us our real life distance of 560 meters. Okay, so that means that I moved another 560 meters. Okay, so let's write that in on my map. Let's make sure that we've got there. So 560 meters. Okay, now it's fairly easy to figure out what our distance was that was covered. All I would need to do is to add up 340 meters, which I traveled in a certain direction, and then 560 meters in another direction. So that's quite easy. My distance, which I traveled, and I emphasize that word, our distance is a combination of those two. My distance was equal to 340 meters down the one street, plus 560 meters, which we found down the next street when we turned left. And if you take a look at that, we moved a total of 900 meters. Now guys, I want you to take a look at this quantity which I've written down. Is this a scalar quantity or is this a vector quantity, and how can you tell? Now, all I can see is 900 meters. If I told you one day I walked 900 meters. Okay, well, it's very good for my legs, but it doesn't tell me where I landed up. So distance is not very useful for telling us exactly where we moved to. I want to know precisely what I managed to achieve. Now, here's the thing which I want to impress upon you. Now, displacement is something slightly different. What I want to do is I want to draw in something called displacement. Now, displacement is the change in position from our starting point to our finish point directly. Very often it's described as the crow flies. Now what that means is if you were a crow, you would be able to fly directly from point A to point B. You wouldn't have to stick to all the streets. This is the path that you would take. Now this is the end achievement of what I've done there. So what I'm trying to say here is that displacement only cares about what I achieved, not how I got there. So this is my displacement. Displacement is a direct measurement from my beginning point to my end point. And I'm going to show you how to do this using a ruler. We can actually figure out what the displacement is, but then we've got to grab a protractor to figure out the direction. And that's an excellent time to start dealing with how to measure direction. So guys, I hope that you're actually doing this on your printed out maps at home, or you're doing this on a screen and you can actually figure out the scale. Now you might notice in the notes that I didn't actually give you a scale like 25 millimeters to 100 meters, because your printers and your screens will all be different sizes. But I left a small key over here for 100 meters over here. So let me just highlight what I'm saying over here. There's 100 meters over there, and that tells me that from that position to that position is 100 meters on your particular map. Guys, you can do this. You can play around with your own scales. See if you come out to the same distance using the map. You should come out to 900 meters distance. Now let's deal with the displacement. Okay, so I'm going to grab my trusty ruler, and we are now going to measure the displacement from the starting point, which was position A, to the end point, which was B. Okay, so now let's see if our ruler is long enough. I'm hoping it is. It might just be. There we go, starting at 0, and then twisting around. Let's actually lengthen it. I'm very, very lucky that this ruler can play around. Okay, but I've got a starting position over here. So there we go, starting at 0. We're almost there. All right, so from 0, we're almost inside there. I think we're 5 millimeters short. Let's just make sure that that lines up very nicely. So that's 0 to 150. And then from that position, I can measure that there is another 5 millimeters. So I've got 155 millimeters on here. So what I'm going to do now is I'm going to figure out how far 155 millimeters is. Now that's not my distance at all. That's the difference in position from A to B. But that's not all. That is not a true displacement. So we're going to have to add something to my displacement, which is going to confuse some people. But I'm going to do this nice and slowly, so you don't need to worry. My displacement on my map, what was the size? It was 155 millimeters. Now I want to know what that was in real life. Let's scale it up. Let's try and find out what the real life distance was, or displacement rather was. So now remember what I said? You divide by 25 millimeters to get rid of the millimeters, the thing that you have. You multiply by the thing which you want, and that was in meters. And what do we get? So let's do this all together. So I say 155 millimeters divided by 25 millimeters, and that gave me an answer there, 31 over 5. Then I multiply by 100. There we go, and I get an answer of 620 meters. So that is my displacement. But it's only the magnitude, guys. There's something missing from this. I want you to figure out what it is. I've only given you how far it was directly from point A to point B. So if you were a bird, if you were a crow, if you were any other sort of bird, if you could fly directly from point A to point B, you would only need to travel 620 meters. This is the distance as the crow flies. But now there's something missing. This is not a real displacement yet. So what I want to do is I want to make displacement into a vector. I've given you the magnitude. Now guys, I want you to figure out the direction. Okay, now that's going to get a little bit more complicated. So this red line which I've drawn on my screen now represents my displacement. I know that my displacement is 620 meters big. Is that correct? Let's just check my value there. So yeah, absolutely 620 meters, and I'm being very good about it. I'm writing it in 620 meters over there. Now, the thing that I need to add to displacement is direction. Now, what I'm going to ask you to do, if you're doing this at home, is I want you to give me direction in terms of bearing. So on this particular map, what I can do is I can indicate which direction is north. I'm actually going to indicate that very nicely over here. North is upwards on this map. So if we've got an upwards arrow for north, and I'm actually going to draw in another line directly from my starting point, that's actually going to help me out very nicely. So north is a vertical line. That is where I find north. So now to measure out my displacement, I need to measure out both its size, its magnitude, and its direction. So guys, I'm going to give you a little bit of time to figure that out, measure it out, and any one of you, maybe post on the page even, start to suggest to us your problems and see if you can figure out how to work with bearing with this particular problem. If you're getting a bearing of more than 90, it looks like you're on the right path. I want you to play around with these notes, guys. But I think it's time for a break so these guys can work it on their own.
Now it's time for a break, so don't go away. We'll be right back. Welcome back from the break. I can't believe that spring is here and soon it will be time to plan for your final exams. Don't stress, exam school is coming in term 4. We'll be here to support you all the way. But for now, let's get back to today's revision lesson.
We're going to jump straight to the difference between speed and velocity. Now, they are very, very closely related to each other. So here we go. The speed is the rate of change of distance. Now, you know this from maths before. If I go a certain distance in a certain time, that is my speed. How quickly I'm covering it is my speed. Now, here we go. Here's the new word. velocity is the rate of change of displacement, or slightly different. But because velocity used displacement, it also becomes a vector itself. So let's take a look at the equations side by side and try and spot the differences. So it says that speed is distance over time, whereas velocity depends on the displacement over time. So now what I'm going to do is I'm going to use the example which we talked about earlier, and we're going to try and calculate what the speed was and what the velocity was. So I'm going to bring up a fresh map so we can scribble a little bit. Okay, and here's some information. It tells me that it took 2 minutes to get from position A, that's my starting point, to position B. Now let's just remind ourselves of some of the vectors involved here. So what happened was I went from A, I moved 340 meters in one direction, then I moved another 560 in another. That means that I moved a total distance of 900 meters. That's quite important. But yet on my map, I found that my displacement was 620 meters. Okay, that was a change in position. So what I'm going to do is I'm going to work out what my speed and what my velocity were. So let's work with the average speed first. Now, you might notice that the equation looks slightly different to how it did before. I'm using symbols instead. So capital S for speed is equal to capital D for distance over delta T. Now, anytime you see this triangle, it just means how much time it took. So delta T. That delta means the change in something. So my speed depends on how much distance there was and the change in time. Now there's a trick to this. I want to see if you guys can figure out what the trick is. I know that my distance was equal to 900 meters. That's the total distance which I traveled. But what about the time that it took? I told you that it took 2 minutes to do this. But I can't substitute 2 minutes. Remember that minutes and hours don't work very nicely. If you guys were watching last week, minutes and hours divide by 60 and all sorts of weird stuff. We need stuff that divides by 10. And there we go. The change in time over there, if I take 2 minutes and change it into seconds, I get 120 seconds. Now let's find out my total speed. Okay, so what I'm going to do is I'm going to grab my handy Casio calculator and we're going to play around with this. So my Casio calculator says a couple of things. So it says 900 divided by 120 seconds, not 1,200. Let's make sure that we don't get too carried away. What that tells me is that I was moving at an average speed of 7.5 meters per second. Okay, so there we go, 7.5 meters per second. Notice how speed doesn't have a direction. I was moving at 7.5 meters per second the whole journey, and that was my average speed. But what about the average velocity? So let's deal with the velocity over here. Now, you might notice some really strange things going on in here in terms of all these weird Greek symbols and all these new letters. Guys, just relax. Okay, the velocity is represented using V. You might notice that there's a tiny little thing on top of it. That little flat line, sometimes you see it inside a textbook. That is the average. Anytime you see this little bar sitting on the top of there, that is the average velocity. That's one of the ways that we can say that this is the average velocity. That means that the velocity could have changed during, but this is the total. So remember what I told you about the triangle? The triangle means the change. So the change in x, which is the change in position, over the change in time. So what was the change in position from position A to position B? Now I use my displacement to calculate my average velocity. So here we go. The displacement was 620 meters. The change in time is exactly the same. It still took me 2 minutes to do that. So now my meters divided by my seconds over there. And let's plop that into my calculator and let's see what comes out. So 620 divided by 120 seconds, I get 5,17 if I round that off. So 5,17 meters per second. Now, I'm not done, guys. I told you that if I use displacement, which has a direction, velocity must also become a vector itself. So I've got to write my answer here with the direction. In fact, I lose marks if I don't give vectors with directions. So I say, therefore, v is equal to 5,16 meters per second. And lucky for us, we worked out the direction a little bit earlier. So we can say bearing of 130 degrees. And there we go. We've got our final answer over there. So there's my final velocity. It's got a magnitude and it's got a direction. Now I want to run you guys through a particular problem that some of the people in my class found it very, very difficult to start talking about, in terms of talking about distance and displacement. Now you might say, okay, well, how far do you walk in a day? Now you might say, okay, well, I kind of walk to school, and then at school I walk around maybe 1 kilometer, then I walk home. I walk around about 9 kilometers in a day. I want you to start thinking about what this means for distance versus displacement. Now, what you've described is many small pieces put together, and I say, okay, well, up to 7 o'clock, I walk to school. Let's say I walk 1 kilometer to school. I walk about 2 kilometers at school, and then maybe 1 kilometer back. I've walked a total of 4 kilometers. That is my distance. Okay, now you've got to be aware of the following. Displacement is something different altogether. Now, my science students, especially my grade 10 class last year, were very despondent about this. What is your displacement over a 24-hour period? And they might say, okay, well, I've got to start calculating this and this. And guys, it's actually really easy. What you've got to do is look at where you are, where you began, where you are, where you finish. That is your displacement. Now, if you take your displacement from 6 o'clock in the morning to 6 o'clock in the morning, it's almost certain that your displacement is 0. And you might say that's impossible, Philip. I move around all day, and I move to school, and I move around at school. I move to this class, I move to so-and-so's class, and then I come home and you say, guys, displacement is only measuring how far you are from your beginning point. If you end at the same place, your displacement is 0. So if I go to sleep, right, 6 o'clock, I wake up. That's where I start. I start my day at 6 o'clock. I stand at my bed and I say, right, I'm going to go move some distance around. And then I get back to my bed. A little bit late at night, I've been marking some papers and I get back in my bed. All of a sudden, I'm back where I started. My displacement has become 0. I've actually achieved nothing, and sometimes it feels like that. I've gone around, I've run around like a man thing, I've achieved absolutely nothing. My displacement is my end change in position. It depends on when you're measuring it. For a 24-hour period, great, there's no displacement. For a 12-hour period, halfway through the day, I'll be very far away from home. And that means that I'm far away from my starting position. So you always measure from your starting position. I just wanted to draw something which illustrated the point very nicely. If you walk a very, very skew path and you end up at a different position over here, the best way to measure your displacement is to take a nice straight ruler, start from your starting position, and measure it directly at the end. It does not take into account the path. A car accelerates from rest to 15 meters per second in 5 seconds. Now, we've got a lot of information, but we're not sure what we're being asked. Now, the first question wants us to calculate the acceleration over that time period. So they are looking for acceleration. Now, a lot of you are saying, okay, now I'm going to start shuffling my way through 4 equations. But you are leading this exploration. You're going in blind. Okay, so what I've got to do is arrange my information. And the best way to do that, get myself a little bit of empty space over there on my page and choose yourself a positive direction. So I'm going to choose the forward direction for my vehicle to be positive. So I'm going to draw in my car over there. So there's my car, and my car is coming over here. Right. So there is my car. Okay, it's a sports car, and it's going to accelerate forwards. So now this is just helping me visualize what's going on. Notice how it's not a beautiful car, but it gets the point across. Now let's start adding the information. It says that it starts from rest. So my V initial is 0 meters per second. Okay, that's nice. What else does it say? Well, it said that it accelerates from rest to a final velocity of 15 meters per second. So I know that when it's over here, I know that my V final is equal to 15 meters per second. All right, that's useful. I know that the entire trip takes 5 seconds. Now, beautifully over here, now all of a sudden I've got a picture inside my head. I know what all the information means. So that is the beauty of this. So what we're going to do now is we're going to calculate the acceleration using the correct equation. But we can only do that after we've done step 3, which is to tabulate. Now, there is a shortcut to be able to tabulate this. Now, I call it the VV tax table. So VV tax. So what I'm doing here is V initial, V final, my change in time, my acceleration, and my x. Obviously, that'll change if you're doing vertical stuff. Okay, so let's fill in what I have. My initial velocity was rest, so 0 meters per second. My final velocity, I knew it was velocity because it said meters per second, is positive 15 meters per second because I decided that forward was positive. Okay, my time is 5 seconds. My acceleration is the equation, or at least the unknown over here. Now guys, here's a bit of a trick. It's a little bit of a hint. After years and years and years of doing this, there is a little bit of a trick to finding the correct equation. Now, I've got my initial velocity, my final velocity, and my time. You need 3 variables to be able to do this. And I've got 3 over there. Now, I'm going to look for an equation which also has a, but before you waste your time, notice how I haven't talked about the displacement. I don't need it. I don't want it yet. So look for the equation which does not have displacement. Ah, okay. All right, now we're getting somewhere. The equation without displacement is far easier to look for than for looking for 4 variables. So look for the equation without displacements. So I'm going to help you. So putting those 4 equations in front of myself, immediately that means that I ignore those 2. I can see displacement as clear as day there. However, this one, and notice how quick that was, there's no displacement inside this equation. So that's beautiful. V final is equal to V initial plus A delta T. Let's use it. So we've done our tabulation. Now we've chosen an equation based on my tabulation. So there we go. V final is equal to V initial plus A delta T. So V final is positive 15. Now notice how I'm emphasizing the positive. It's heading forwards. Guys, these are vectors and direction is shown by the sign. Plus means forward. So over here, V initial, 0, plus A times delta T. It took 5 seconds. Now, guys, please practice your skills when you are trying to manipulate this. So this leaves me with 15 is equal to 5 times delta T. To get delta T on its own, I divide both sides by 5. Please don't subtract it, that's incorrect. Divide both sides by 5, and what I'll get is that 3 is equal to delta T. So therefore, delta T is equal to 3 seconds. Now guys, one final warning. Always put a unit on your final answer or it's wrong. I can't say that it takes 3 minutes, 3 hours, 3 seconds. Okay? So, apologies. I've actually gone down the wrong path here. I hope you guys noticed. What I've written down here instead of delta T over here, we were actually after delta A. I hope you noticed that. I only noticed this now. Is that we were dealing with 5A, so 3 is equal to A, and A is equal to 3. And it's not seconds, guys. So please make sure that your units are correct. Now this is acceleration. So what is a unit for acceleration? I hope that you noticed from earlier on in the show, that is meters per second squared. But now there's still something missing from my acceleration. It's positive 3. Now acceleration used velocity, so that means that acceleration is also a vector. So vectors need a unit and they need a direction. So 3 meters per second squared, forward. Okay, so I hope you don't mind that little mistake, but the important thing is that you catch your mistakes. You won't ever stop making mistakes. Sadly, I still make them, you can see, but it's important that you go back and fix them and you get better and better at that. Now let's answer our very last question. I think we've got a few minutes left. It says, calculate the displacement during this acceleration. Okay, now this is another point at which I'm going to tell you a really important tip. I now know what the acceleration is. I'm going to write it in. I know that I'm accelerating at 3 meters per second during that time. Now you might say, okay, well, yay, that helps me out. I can use acceleration. Guys, please don't use your acceleration because it's calculated. It could be wrong. So what I'm going to do is now I'm going to look for an equation without my acceleration. So without acceleration. So I'm looking for something with all the other equation pieces that I need and without acceleration. And if you do this really quickly, I'm going to have to do this quite quickly because we're running out of time. Delta x is equal to vi plus vf over 2 times delta t. You'll notice that there's no acceleration anywhere inside here. So let's do this quickly. I know that v initial is 0 plus vf is positive 15. My time period is 5. And then I divide that all by 2. So now when I put this in my calculator, the really nice thing about our calculator, the Casio calculator, is that it can do fractions directly for us. So on top of this, I would say that I've got 0 plus 15, close my brackets, multiplied by 5. And what do I have to do to that answer? I have to divide it all by 2. There we go, and I get a displacement of 37,5, and that is my final answer. But I'm not out of the woods yet. I haven't done all my job yet. I need to give it a unit, displacement's measured in meters, and it's a vector, so it needs a direction of forward. So I hope you guys...
We've come to the end of today's show. Thanks for joining us and for chatting to me during the show. Remember to visit our website, learnextra.co.za/live to get the notes and to watch the videos from the term. If you are stuck on any questions, make sure you post them on Helpdesk at learnextra.co.za/helpdesk. From all of us at Learn Extra, have a great September holiday and join us again from the 30th of September for Term 4.